Good morning once more. It's my privilege to introduce to you a remarkable mathematician and expositor, Doris Schattschneider, who will tell you about another remarkable person. Doris, as you know, is famous for her work and her writings on tessellations, and, as you will find out tomorrow night in Decatur, about M.C. Escher. But today, Doris will tell you about Marjorie Rice, and I am sure you are in for a wonderful treat. Doris?
The story of Marjorie Rice is really a remarkable one, and I'm very pleased that I'm able to share it with you. So I don't forget at the end, let me mention that there will be an article coming out in the Journal of Mathematics and the Art about Marjorie and much more details than I can give you today of her story. Marjorie was born in 1923. She grew up on a tiny farm in southern Oregon, went to a one-room schoolhouse, and she said that she had wonderful teachers who encouraged her. She said, "Arithmetic was easy for me, and I liked to figure out why we used the methods we did." Sounds like a budding mathematician to me. Her family moved to Florida when she was in high school, and she pursued the secretarial track, which at that time only allowed her to take one mathematics course, and that was general mathematics. She always had regretted that she never went beyond that. She also had a great interest in art, as you'll see later. The story of Marjorie and Martin Gardner begins in 1975, when Gardner wrote a column in the July 1975 issue of Scientific American, and it was titled "On Tessellating the Plane with Convex Polygon Tiles." And in that article, he, of course, said that any triangle can tile the plane, and any quadrilateral can tile the plane, even non-convex ones. And these tilings that I'm showing are easily generated simply by rotating 180 degrees about the midpoints of the sides of the polygon. So any triangles, any quadrilaterals can tile the plane. Gardner's column went on to review what else was known. Only 3 types of hexagons can tile the plane. This was discovered by Carl Reinhardt in 1918 in his doctoral dissertation. And here there are the conditions on angles and sides of these hexagons. These are not single hexagons, but infinite classes of hexagons that are characterized by these conditions on sides and angles. And these 3 tilings are not the only tilings that they make. These are just representative tilings where those angle and side conditions are necessary. He also mentioned that no convex polygon with 7 or more sides can tile the plane. This was kind of a folk theorem, and when I actually tried to find out more about this, could not find it in writing anywhere, published anywhere, and Ivan Niven then wrote a paper with the proof. Gardner also mentioned that Reinhardt had also discovered there were 5 classes or types of pentagons that tile the plane. Again, each type characterized by conditions on angles and sides. And these were called type 1, 2, 3, 4, and 5. Type 1 was the most general. Any pentagon with 2 parallel sides, they don't even need to be congruent, can tile the plane in the manner that's shown. And then the reason for his article was because he wanted to advertise the fact that R.B. Kirshner in 1968 had published an article in the American Mathematical Monthly saying that he had discovered 3 more types of pentagons that tile the plane. These were not quite in the same type that the previous ones were. In order to tile the plane, you had to stick 2 of them together, and then that block of 2 could tile the plane in a manner that was called transitive Tilings are transitive or isohedral is the more modern word. If given a single tile, if you act on it by the symmetry group of the tiling, it can fill the whole plane. And another way of saying it a little bit more mathematically is that the orbit under the symmetry group, the orbit of the one tile, there's just one orbit. For a two-block transitive, there would be two different orbits. Then Kirshner went on to say, this completes the list, and went on to say, the proof that the list here is complete is extremely laborious and will be given elsewhere. Mathematicians in the audience know of another mathematician who made a similar comment one time in the margin of what he wrote. Within a month, Martin received a letter from Richard James III, and it showed that he had found a new pentagon that was not in the list of 8 that tiled the plane, and Martin published this in his December 1975 column in the addendum. He often did this, as you know, that would do some follow-up in later columns. And how had James found this? Well, you all know the standard tiling, the Archimedean tiling by octagons and squares. And if you divide one of the octagons with 2 perpendicular lines, that makes 4 congruent pentagons. You can pull those octagons apart, and then in the in-betweens fit congruent pentagons. So this was a new tiling, but those particular tiles have 2 parallel sides. And as I said before, that was type 1. So this was not a new pentagon. But if you twist that X in the middle of the octagon, you do get a new type. And so this indeed was a new type. And even more surprising was that it took a block of 3 pentagons to tile the plane transitively. And so this is called a 3-block tiling. It also was not edge to edge. You can see over here where there's a vertex of the tiling, but it meets at a point that is not a vertex of the tile. I found out about this tiling long before Gardner published it. And so I want to make a little aside here about something. By the way, these are the general conditions on this tile. Here's my aside. It's called mg squared for Martin Gardner's mathematical grapevine. Many of you in the audience are part of that or were part of that grapevine. It went like this for this story. Richard James sent his discovery to Martin Gardner. Martin Gardner, in turn, sent it to several mathematicians for verification. One of them, the famed geometer H.S.M. Coxeter. I happened to visit Coxeter that August, and he had just received James's discovery from Gardner. And Coxeter said to me, I think you might be interested in this. So he showed me the single tiling that James had sent to Gardner. And on the way home on the plane, I thought, I think there's more than one here. I think this is a whole class. And so I worked it out and worked out the general conditions, which in turn then I sent to Gardner. And he thanked me very much for that. And then as a result, he then published it in the December Scientific American. So at that point, Gardner knew I was interested in pentagon tilings, and so this is how I got involved in this whole pentagon story that I'm going to tell you. Marjorie Rice, at the time, was a 52-year-old homemaker living in San Diego. Her husband was a printer. She was raising 5 children, some of whom were still at home. And her youngest son, Robin, had a subscription to Scientific American. What the family didn't know was, of course, Marjorie got the mail first, and Marjorie was an avid follower of Martin Gardner's column. None of her family was aware of this. When she saw that December 75 column about Richard James's discovery, she thought, maybe I can find some new pentagons that tile the plane. So she set herself the problem of finding other types of convex pentagons that can tile the plane and finding new tilings by convex pentagons. And she set out on this investigation that actually went on for over 20 years. She did it at home, at her kitchen counter, when no one was there. Her family did not know she was doing this. Whenever someone came home, she'd shove it in the kitchen drawer, and only much later did they find out about it. How did she begin? Remember, she had no geometry course at all in her background. This is how she began. This was her inventory of the known tilings. And so she developed her own notation, and it's symbolic. It's visual, it's symbolic, and it really even does away with labels, if you wish. Each of these little house-shaped pentagons represents a class, a type. And when you look at these arcs or lines inside, they're telling you what angles come together at a vertex of the tiling. So this is type 1. The three angles A, B, C come together at a vertex. And this straight line means that B and E, those angles add up to 180. And so on. Here you would, down here in this lower corner, this would be type 6. You have something looking much more complicated. You read this as 2 times angle A, or 2 angle A's, plus angle E adds to 360. And here she's told you with the letters AAE, that's shorthand for an equation, 2A plus E equals 360, and so on. Here this would be 2 angle C's plus angle D plus angle B come together in the tiling. And again, here that's written BCCD, meaning that that is an equation, B plus 2C plus D equals 360, and so on. So here she inventoried in her own way, making up her own symbolic notation, what was known, and then she went on to try to find others. Within a few months, remember, this was the December 75 column for James's discovery. February 1976, she sends a letter to Martin Gardner. Dear Mr. Gardner, here's a pentagonal tile that I believe really is different from any you had listed, though similar to type 7 and 8. Those were 2 of Kirshner's. Sincerely, Marjorie Rice. And she actually, these are actual photos of her drawings of 2 different versions of the same tiling. This one in the lower left has the pentagons have sides in golden ratio. And she also here showed the range of shapes that pentagon could take, going from a square to a quadrilateral and all the shapes in between. And here are the angle conditions. Very similar to those of Kirshner 7 and 8, but yet new. Gardner sent this to me and said, would you please check out that this is true, that this is new, and if so, let me know, but please correspond with her directly from this point on. He didn't want to be middle person, and but keep me apprised of what's going on. He also, for whatever reason, decided not to publish this, so this was not published in Scientific American as a follow-up to his December 75 column. When I received that, I came up with a conjecture. Mathematicians do this all the time. Both Kirshner's, 2 of Kirshner's and Marjorie's all had this property that any pentagon having 4 equal sides containing 4 different angles, such that twice one angle plus another, and twice a third angle and another, all add up, each of these add up to 360. I made the conjecture that these conditions would provide a pentagon that tiled the plane. And I figured that might keep her busy for a while. Well, a week later, she writes me and she wrote a very, very polite letter. I must say this. I've summarized this in very terse terms. The conjecture's false. There are exactly 4 distinct types of pentagons, as described in the conjecture, that do tile the plane, and 2 distinct types that do not. And here was her explanation. No words. This was it. So this was the first time I had seen any of her notation, and I had no idea of what these pentagons with chicken scratches in them meant. And obviously I had to figure it out, and I finally did. And so here she's explaining visually that here's one that doesn't work. The ones that are circled do work. The ones that are, here's one that doesn't work, and the reason is that the types could only use the equations given, not anything else. And if you put 3 of these pentagons together that satisfy, I'm having a little trouble finding my, look at number 2. And you see where her little arrow points to AA. If you put 3 of these pentagons together, where you have 2E and a B coming together, that's one of the conditions, 2E plus B equals 360, then that forces 2 angles A to come together at a vertex of the tiling, but that's not one of the equations. So in other words, you're throwing in more equations being necessary. And so there were 2 examples, here's this one and this one over here, where that throughout that is a possibility. But then there was this. I thought, what does this mean? And I finally decided, after fooling around, trying to construct pentagons that satisfied these conditions of 3 and 4, that in fact it's non-constructible. It is degenerate. It's just a quadrilateral. And that was her way of showing that. She couldn't prove it, but she'd obviously tried to construct it and found she couldn't. Later, I proved it, but only using the law of sines and cosines for higher than triangles, for polygons. So it was a non-trivial kind of condition. From March to November, Marjorie went through listing symbolic marked pentagon tiles, checking to see which angle combinations were feasible. And for each of those that seemed feasible, she actually drew up a tiling. And then she refined her search. She increased her collection of tiling several times, mailing me all these things. My mailbox would always have letters and examples from Marjorie. She went from 26 tilings in March to 58 tilings in October. She also adopted notation for the kinds of tilings. P1 meant a tiling in which angles of the pentagons were only used once. So this was types 1 and 2. P2 was pentagon tilings where each angle was used twice in the set of defining angle equations. And here was her inventory of, her first inventory in March of 12 of these P2 classes. And then for each of these, she drew up tilings. In these pictures, I realized that her notations are very hard for you to see, but she not only drew the tilings, but she gave the conditions on the angles that had to come together. And also, just looking at the tiling, you can figure out which sides of pentagons had to meet each other. The dark tiles are the reflections of the light tiles in these pictures. And in the lower left corner, you have Marjorie's new discovery. That later became called type 9 rather than type 10, even though James's came first, because it was so like Kirshner's. So now there were 10 known types. In August 1976, I sent Marjorie a draft of an article that I was writing about tiling the plane with congruent pentagons for Math Magazine, and she noticed that the two block tilings by Kirshner and her own tiling looked very much like they were formed by what she called double hexagons that were split into pentagons. And so she noted that these double hexagons could tile in 6 different ways. And up at the top of the page, you see that these are the various ways she said that you could split up these double hexagons into 4 pentagons. And she pursued this idea with a vigor. In October, she makes a new inventory of pentagon tilings, and this time they were sorted differently. It included all the known types and many new 3-block tilings. In December, she discovered 2 new types, 2 brand new types. And if you look at the tilings here, I think you can see that these double hexagons, this idea really worked. This, again, is a photograph of her actual drawings and conditions on the tile. So these were to be called types 11 and 12. In 1977, I sent her a technical paper by Grunbaum and Shepard, the 81 isohedral tilings of the plane. And she looked at the tilings where the tiles had 5 vertices, so they could be pentagons. Grunbaum and Shepard had done their original research in a very technical manner, drawing just symbolic straight-edged tiles and marking them so that you could identify how edges met each other. Marjorie, when they published their paper, though, they said, this looks pretty complicated, so let's draw the tilings with curved edges. So just by looking at them, you can pretty well see which edges match which edges, and also S-shaped curves if a particular edge is related to an adjacent tile by a half turn or 180-degree rotation. Marjorie took some of these pictures and did this to it. She basically reverse engineered what Grunbaum and Shepard had done. To her, the symbolic representation of these tile relationships in these various tilings was easier to understand. I found that absolutely fascinating. And now she extended her list of 2-block pentagon tilings, this time up to 56 possibilities, sketching more than 100 different tilings. And in December 1977, she discovered yet another new tiling pentagon, to be called type 13. And it was just in time that I could sneak it into the article for Mathematics Magazine. Marjorie had always been interested in art and took some correspondence courses in those days. And she loved the work of M.C. Escher. And she decided that she would use some of her pentagonal tilings as underlying grids for Escher-like tessellation. And so I want to show you some of these that she made. This particular grid is with unique mirror symmetric type 2 equilateral pentagons. And in each pentagon, she put 1 hibiscus. She knew exactly how the surrounding tiles had to meet that. She was completely cognizant of the tile relationships. And so here's her tiling based on this grid. Quite a beautiful tiling. And the coloring itself is interesting. The pentagon in this pentagon tiling is displayed in 8 different rotated positions. And so she colored her hibiscus in 8 different colors to mark those positions. This, by the way, is something that Escher also did with some of his tessellations. Here's another different tiling, a 3-block tiling by another equilateral type 2 pentagon, this time filled with shells. And here's a type 2 pentagon that gives you a mess of fish. Each pentagon holds 3 fish. And her last type 13 pentagon, she turned into a tessellation by butterflies. In between all of this work on pentagon tilings, Marjorie got a copy of Grunbaum and Shepard's famous book, Tilings and Patterns, and in that she learned and then went off on a tangent on her own about non-convex pentagon tilings, aperiodic tilings, and she sent me a bunch of stuff on that. I'm not going into that, but I want to pick up again on the pentagon tilings. In March 1993, I sent Marjorie output from Daniel Hewson's computer program that he called RepTiles, and this showed topological or combinatorial output on all possible edge-to-edge 2-block and 3-block tilings by pentagons. And this particular slide shows you 12 of the 3-block tilings by pentagons. And you're going to probably say, those don't look like pentagons to me. We're going to look at this one, number 56, more closely. In fact, the program purposely drew the 3 different pentagons in very simple form so that they would not look congruent, so that you could easily identify visually the 3 different tiles made up a 3-block. And so what she decided to do was, since these were supposed to be tilings by pentagons, to try to decide which of these could be by congruent pentagons. None of the output had congruent pentagons. And just to give you an idea of the scope of this investigation, if you want to make a 2-block of pentagons, well, you fix the angles, fix the labels of angles in one pentagon, and then there's 10 different ways to stick another pentagon on that. There were 23 2-block tilings, so there's 230 cases to check. For 3 blocks, it's even worse. Here in the 2-block, she did manage to find many, many new tilings, but no new types of pentagons. And all of the earlier 2-block tilings she had found in her own way showed up in this search. But here's for the 3-block tilings. For each possible 2-block, remember there were 230 of possibilities there. If you stick a 3rd tile to make a 3-block, there's 10 more possibilities for that. So it's 100 possibilities for each possible pentagon. And there were 43 different tilings. That's 4,300 cases. And she examined every one of them by hand. What did she do? Well, she created a 10 by 10 grid for each of the 43 cases to record what was possible. And let's look at this one case, 56, because this becomes very important, as you'll see. Here, as I said before, it looked like this. Here we have a block of 3, and one of them looks like a triangle, one of them looks like a quadrilateral, and one actually looks like a pentagon. But if you mark the vertices of the tiling, as I've done here in red, and I hope the red shows up for you, you will see that each of these tiles is surrounded by 5 vertices. So topologically, it is a pentagon. Here, you can see that there's a 3-fold rotation. That is, these 3 tiles are related by a 120-degree rotation about this corner. So this angle has to be 120 degrees. And down here, you see these 6 tiles rotating about this point, and they're all congruent. So this angle down here must be 60 degrees. So you already know that 2 of these angles, you already know 2 of the angles of the pentagon. One has to be 120 and one has to be 60. Here's her analysis of that one tiling, filled in. I don't expect you to be able to read this, but possibly you can see there's a lot of X's. In fact, there's 99 X's. That is, either this pentagon doesn't exist or it can't fulfill all the conditions of that topological tiling. But there was one success, one check mark, one particular success. And here's a blow-up of that cell. So she knew that there was a 120-degree angle, knew that there was a 60-degree angle, and examining the topological tiling could figure out the other angle equations, and then was able to, once you write down these angle equations, you in fact find out that the angles are totally determined as well as the sides. So here's a blow-up of that single 3-block, and there's the picture of the pentagon that comes out of her analysis. Very beautiful pentagon. I'll talk about that in a minute. But this yielded a very beautiful new tiling by congruent pentagons. She called this tile a versatile. And there's the tiling. You can see it's quite interesting, quite beautiful. It has 60-degree rotations, 120-degree rotations, half turns. And there's the actual tile. This tiling it's a 3-block tiling, obviously. We mentioned that before. This block that I've drawn up can generate the whole tiling by rotations about 3 different centers. And if we rotate about the 60-degree angle, we fill out what looks like a large snowflake. If we rotate about the circle, which is a 180-degree rotation, we get an adjacent snowflake. And then if we rotate by 120 degrees about the little triangle that I've shown, we fit the 3rd snowflake, and you can keep going and fill the whole plane. If you want to just begin with the snowflake of 18 pentagons, that will actually tile the plane by translation. And in 1999, the Math Association of America installed this tiling in the foyer of its headquarters building. They were going to renovate the foyer, and someone came to me and said, you know, we want an interesting tiling, and what do you think about a Penrose tiling? And with apologies to Penrose, I said, oh, everybody has Penrose, so. I said, do you want something really unique, something really new? And so I told them about Marjorie Rice's tiling, sent them pictures, and they said that would be wonderful. So the tiles had to be fabricated, and they were done. We have a tile fabricator in Bethlehem. They were fabricated and glazed and then installed by this same company. There was a dedication of the foyer. Marjorie was invited but couldn't come, so I went in her place, and she was sent this certificate of recognition. She also made this beautiful tessellation of roses based on this tiling. And I'd like to mention that her tessellations were on display in 1998 in Rome as a part of the celebration of the centennial of Escher's birth. So Marjorie, who is a very shy, very unassuming person with little mathematical background, really made some enormous mathematical contributions. And I wanted her to know how she was appreciated by the mathematical world. And so in 1995, I was invited to give a talk in Los Angeles at a regional MAA meeting, and invited her and her husband to come along, and they did. And I had said, Marjorie, do you think you could stand up and say a few words about your work? She said, oh, no, I absolutely could not do that. And I said, well, if I introduced you, could you at least stand up? And she said, I think I can do that. So I gave my talk, and at the end of the talk, I said, we have someone very special in the room for us today, and I'd like to introduce you to Marjorie Rice. And so very hesitatingly, she stood up, and in one swoop, the whole audience stood and gave her a thunderous ovation. And I was so happy that she and her husband finally knew how much the mathematical world really appreciated what she did. A few years later, I received this poem that was written by one of her fans, and I'll just let you read that. I don't want to read it myself. I'll just let you read it for a minute, and then I want to finish up the Pentagon tiling problem. The tiling problem lay dormant for many more years after her discovery in 1977. But in 1985, Rolf Stein, a graduate student, discovered a single unique pentagon that tiled, and I put this on the cover of Mathematics magazine. This became type 14. And a little later, in 1987, Martin Gardner published, as he often did, a collection of his past columns of mathematical games with addenda. And in his addenda to the chapter on his 1975 column, he not only published Marjorie's Type 9 Pentagon that she had sent him back in 1976, but also updated to the current state of the Pentagon tiling problem at that time. He was even able to mention Rolf Stein's discovery. He used the term Marjorie Rice's fantastic achievements, and I think that was quite suitable. In 2015, very recently, as you probably all know, Type 15 was discovered. It was another unique single tiling pentagon. And this was discovered via a computer search in which the computer was testing various combinations of equations that could occur to produce pentagonal tiling. Not terribly unlike what Marjorie did by hand. And this one pentagon showed up. Here's a little bit of its tiling. You can see by the coloring I've put there that this is a 3-block tiling. And although the computer didn't do it, I gave you what Marjorie would have put down as its symbolic representation. In 2017, Mikhail Rao announced that he too had done a computer search and was announcing that Type 15 was indeed the last, that the list of tiling convex pentagons was now complete. As of the latest information I have, that has not been independently verified, although most people I've spoken to, including those who have on this screen, Casey Mann and his crew, they really feel that this probably is the case, but it still needs independent verification. In your gift exchange, you'll see how you too can construct the versatile for what I call the MAA tiling. And it's a beautiful construction, something you could have done. So here's how to make it. And not only do I tell you how to make it, but I give you some tiles to put together and challenge you to find as many different edge-to-edge tilings as you can with this tile. And one simple way to find some is to try to form with 2s or 3s or more blocks of these pentagons what are called generalized parallelograms, that is 2 parallel and congruent edges, or 3, this would be called a par hexagon, 3 pairs of congruent and parallel edges. So I wish you fun with the versatile. See how many tilings you can come up with. To summarize about Marjorie, some of the amazing things about what she did. She had no higher education in mathematics. She She addressed a mathematical problem about tessellation. She developed an ingenious method of investigation. She invented a unique notation. She used visual means to record her findings. She obtained significant mathematical results, and her mathematical investigations led to ingenious tessellation. Quite a remarkable woman, don't you think? I can change these pronouns to he. And who would that be? MC Escher, tomorrow evening, Decatur Presbyterian Church, 8 p.m. Thank you.